questions 8 through 10 on the 2004 grade 12 Euclid math contest. If t is equal to x squared plus 1 over x squared, determine the values of b and c so that x to the power of 6 plus 1 over x to the power of 6 is equal to t cubed plus bt plus c for all non-zero real numbers. So we have t is equal to x squared plus 1 over x squared, like that. And we have x to the power of 6 plus 1 over x to the power of 6 is equal to t to the power of 3 plus b times t plus c. All right, I guess we have to substitute this into here. And before I do that, I'll just add the fraction there. So this looks like if you multiply top and bottom by x squared, you get a common denominator, x to the fourth plus 1 over x squared, like that. Okay, now let's substitute t into this equation right here. So I have got x to the power of 6 plus 1 over x to the power of 6 is equal to x to the power of 4 plus 1 over x squared, all to the power of 3. And then I've got b, and then in brackets x to the power of 4 plus 1 over x squared plus c. So now I have to expand this equation. So let's do that. Going to need a lot of space here. So on this side, I'll just add the fraction here, multiply top and bottom by x to the power of 6. So I get x to the power of 12 plus 1 all over x to the power of 6. And on this side, I've got to expand this. All right, a lot of fun. X to the power of 4 plus 1. And then I've got x to the power of 8 plus 2 times x to the power of 4 plus 1. And that's all over x to the power of 6. And then this one, bx to the power of 4 plus b all over x to the power of 2. And this is just c over 1. C over 1. Now I'm going to get a common denominator so I can get rid of the denominators. Multiply top and bottom here by x to the power of 6. Multiply top and bottom here by x to the power of 4. Okay? And if I do that, my denominators will all be the same. They'll be x to the power of 6, so I can get rid of them. And that just leaves me with x to the power of 12 plus 1. Expanding this is x to the power of 12 plus 2 times x to the power of 8 plus x to the power of 4 plus x to the power of 8 plus 2 times x to the power of 4 plus 1. Okay? Plus b to x to the power of 8 plus b x to the power of 4, and finally a c x to the power of 6. All right, we got this far, hopefully without making any algebraic errors. Now let's see what happens. X to the power of 12, those cancel, the 1's cancel, and then this becomes 0. And I think at this point we have to group like terms. Okay? I've got 2x to the 8th and 1x to the 8th, so that becomes 3x to the 8th. And then what else do I have? I've got, let's see here. Oh, I've got a b, okay? A bx to the 8th as well, okay? And then x to the 4th, I've got a 1 and 2 and a b. So I've got 3x to the 4th plus bx to the 4th, like that. And then finally this lone cx to the 6th. Factor out an x to the 8th, and I've got 3 plus b. Factor out an x to the 4th, and I've got 3 plus b. And then cx to the 6th. If I factor the 3 plus b, I got x to the 6th, x to the 8th, sorry, plus x to the 4th, plus cx to the 6th. And I think that's about as far as I can go. And this is equal to 0. So if that's equal to 0, that must mean that this is equal to 0 and this coefficient is equal to 0. So if 3 plus b is equal to 0, that means b is negative 3. And c has to be equal to 0 in order to make that x to the 6th disappear. And therefore that's it. Those are the values for b and c, which is what the question wanted us to figure out. If x is a real number satisfying x to the power of 3 plus 1 over x to the power of 3 is equal to 2 root 5, determine the exact value of x squared plus 1 over x squared. So first, let's just deal with this, figure out what x is, and then we can substitute it into there and get a numerical value for that expression. So how do we want to proceed? Let's see here. Do I want to... I might as well. Just to make things a little bit easier, I'll let x to the third equal a. You don't have to do that, but I just figure what the heck, right? I mean, makes it a little bit easier, I think. And then in the end, you can always substitute back. So our equation becomes a plus 1 over a is 2 root 5. All right, we've got some experience now of adding fractions like these. So I got a squared plus 1 is equal to, over a is equal to 2 root 5. And then cross multiply, I've got a squared plus 1 is equal to 2 root 5a. And then put everything on one side, a squared minus 2 root 5a plus 1 is equal to 0. And at this point, this looks like a quadratic, correct? And if it is a quadratic, I can probably just use a quadratic formula unless this factors. Does it factor? I don't really know. It doesn't look like it. That's okay. I'll use a quadratic. It's not going to be that painful. A is equal to minus b plus or minus the square root of b squared, so minus 2 root 5 all squared, minus 4ac. All right? All over 2a. Don't forget that. So this looks like 2 root 5 plus or minus. The 2 root 5 squared would be 4 times 5, which is 20. And then 20 minus 4, which is 16. So the root of 16 all over 2. And okay, this looks like it will be a pretty decent looking number because that'll be 4. And then if I divide by 2, I'll get root 5 plus or minus 2. All right, good. But remember, this is a. We let x to the power of 3 equal a. So this is x to the power of 3. That's equal to root 5 plus or minus 2. So that means that x to the power of 3 is equal to root 5 plus 2, or x to the power of 3 is equal to root 5 minus 2. And therefore x is equal to root 5 plus 2, the cube root basically, the power of 1/3, same thing. And in a very similar way, x can also be equal to root 5 minus 2, the cube root of that. All right, great. We've got two numerical values for x, and now we can solve for this guy right here. X squared plus 1 over x squared. All right, let's see what we get. Okay. So we have to figure this out now. X squared plus 1 over x squared. I guess we can just substitute it directly, right? There's no reason to simplify. Let's first start with this guy right here. Root 5 plus 2 to the power of 1/3, and this is going to be all squared, plus 1 over root 5 plus 2, all to the power of 1/3, and that's all squared. Okay, I guess you just take out your calculator and figure this out. And if you do, you'll get a value of 3. Yeah, try it. Take out your calculator. At this point, it's just numbers. There's no variables anymore. And in a very similar way, if you use x equals root 5 minus to all to the power of 3, you will get also an answer of 3. So that expression is equal to 3. A Kirk triplet is a triple xyz of integers such that x is greater than z. Z is a prime number, and there is a triangle ABC with AB equal to AC equal to x, BC equal to y, and a point D on BC such that AD is equal to Z, and angle ADB is 60 degrees. Part A, find the Kirk triplet with x equal to 7 and z equal to 5. So our triplet is of the form x, y, z, and they have already given us x as 7 and z as 5. And they want you to obviously figure out y. Now let's see if our conditions are met. Is x greater than z? Yes, it is. 7 is greater than 5. Is z a prime number? Yes, it's 5. So obviously we have to now concentrate on the third condition. And the third condition is this diagram right here. And the third condition tells you that this angle here is 60 degrees. This one right in here. And if that's the case, then this angle has to be 120. Right? Because angles about a line are equal to 180, the sum of them. And therefore, this is going to be a law of cosines, because we've given two sides of a triangle and we've been given an angle. So that definitely screams law of cosines. So here we go. The first triangle that I will look at is this one right here, ABD. And I will use obviously 60 degrees since that is the angle they've given me. So we've got 7 squared is equal to 5 squared plus BD squared minus 2 times 5 BD cos 60. So this is 49 is equal to 25 plus BD squared minus 10 BD, and cos 60 is a half. So there you go. And now let's put everything on one side. And we've got BD squared minus 5BD, like that. And then 25 minus 49 is minus 24. All equal to 0. Now does this factor, I believe it does, BD 8 and 3 minus plus, like that. So BD is equal to either 8 or negative 3. Well, obviously it can't be negative 3 because BD is a distance. So therefore BD is equal to 8. In a very similar way, we will do the exact same thing on this triangle right here, ADC, like that. So again, law of cosine, 7 squared, because x is 7, plus is equal to 5 squared, plus DC squared this time, minus 2 times 5 DC cos 120. So this becomes 49 is equal to 25 plus DC squared minus 10 times DC, and cos of 120 is negative a half, like that. So this becomes DC squared, and this would be plus 5 DC. 25 minus 49 is minus 24. And then this should factor as well, DC, DC, 8 and 3, but this time plus and minus, and therefore DC is equal to 3 or negative 8, and obviously since it's a distance, DC is equal to 3. Now what is y? Y is basically equal to BD plus DC, right? And BD we just figured out was 8. DC we just figured out was 3. So y is 8 plus 3, which is 11. So this is 7, 11, and 5. There you go. That's the Kirk triplet that meets these requirements. Part B. Determine all other Kirk triplets with z equal to 5. So now they want us to determine every single Kirk triplet that we can find where the value for z is equal to 5. So we have to now figure out x and y. All right, in a very similar way, we can use this triangle, 60 and 120. So on triangle ABD, this one right here, we can use law of cosines. We've got x squared is equal to 5 squared plus BD squared minus 2 times 5 BD cos 60. All right, so this is x squared is equal to 25 plus BD squared minus 10 BD, and then cos of 60 is a half, 0.5. So this gives me x squared is equal to 25 plus BD squared minus 5 BD. And that's about as far as I can go because I have two variables there. All right, let's do the same thing, but this time on this triangle right here, ACD. So I've got x squared is equal to 5 squared plus DC this time minus 2 times 5 times DC cos of 120. And this gives me x squared is equal to 25 plus DC squared minus 10 DC, and then cos of 120 is negative a half. So like that. And this takes me to x squared is equal to 25 plus DC squared plus 5 DC. And that's about as far as I can go there. Well, the good news is I've got two expressions for x squared, and therefore they must be equal to each other. So that means that 25 plus BD squared minus 5 times BD is equal to 25 plus DC squared plus 5 DC, like that. Now, at this point, the 25s go, and this just leaves me with BD squared minus 5 BD is equal to DC squared plus 5 DC. Now, unfortunately, that doesn't help me solve for anything in terms of a numerical value, but it does give me a little bit of a relationship, right? But how do I proceed from here? Well, we know that y, if we go back to our diagram, this y that they've given us is BD plus DC, right? Y is equal to BD plus DC. So let's substitute that in. Maybe that will help us. I'm pretty confident that it will at least give us a relationship that we can use. So, which one you want to use doesn't really matter. Let's just say DC is equal to y minus BD. Okay, and let's substitute that into here. So we get BD all squared minus 5BD is equal to, we got y minus BD all squared plus 5 times y minus BD, like that. Expanding, we have BD squared minus 5BD on the left side. On the right side, we will have y squared minus 2y BD plus BD all squared plus 5y minus 5BD, like that. And let's see what cancels here. The BD squareds go. the minus 5 BD goes, and that just leaves me with 0 is equal to y squared minus 2y times BD plus 5y. All right. If I divide through by y, since everything has a y, this just leaves me with minus 2BD plus 5. And I can isolate for BD. It would be basically y plus 5 is equal to 2BD, and therefore BD is equal to y plus 5 over 2. All right. So this is going to help us now, this equation. Because since we have BD in terms of y, we can substitute it back into this one right here. This equation right here. We have BD in terms of y, so we can put our value of y in there, and that will definitely help us solve for x and y. So that equation is x squared is equal to 25 plus BD all squared minus 5 times BD. So x squared is equal to 25. BD, I will put in my value of y, or my expression in terms of y, and minus 5 BD, y plus 5 over 2, like that. So this becomes x squared is equal to 25 plus y plus 5. I will expand that. Y squared plus 10y plus 25 all over 4. And minus, let's see, I'll expand that as well. 5y plus 25. I'll keep it in brackets for now, all over 2. Let's get rid of these fractions by multiplying everything through by 4. That should do it. So this is 4x squared. This is 100. This is y squared plus 10y is plus 25. And then multiplying through by 4 there, it becomes 2 times that. So minus 10y and minus 50, right? We take it out of the brackets. So let's see what goes here. 4x squared is equal to y squared. Oh, the 10y's go. Okay, that's helpful. Then I've got 100 plus 25, 125 minus 50, 75. All right, this is my relationship between x and y. Okay. All right, and at this point, I believe we're going to have to make a table. And my table is x, y, z, of course. Those are the numbers I'm interested in. Z, they give us already, right? They tell us that z is equal to 5 for everything. So I'll just write z equals 5. And we have to figure out x and y. Then they have to be integers. Now, one of the conditions, if you remember, is that x is greater than z. So if that's the case, and x is an integer, we start with 6. We can't go anything lower than that. And if we do, and we use this formula, you can easily plug in 6 for x. You get y is equal to 8.3. So that's no good, unfortunately. 7 was the one we figured out in the previous question, remember? That was 11 and 5. So this works. But we already figured that out. That's nothing new. And you keep doing this for 8, 9, 10, 11, and so on until you get a integer value for y. And I'll let you do this. I'll spare you the pain of listening to me do it. And what's interesting about this question is that they tell you, I'll read it for you again, is that determine all other Kirk triplets, right? All, emphasis on the word all. Well, how long do they want me to keep going here? I mean, I can keep going forever, right? There's no limit as to how large x can be. So if you do this, you'll find that you don't get integer values for 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Finally, you get an integer value of 37 when x is 19. And of course, z is 5 for all of them. So this is the only one. I think in the question, if they had said, find the only other Kirk triplet, then once you get to here, you say, oh, okay, finally, I got the only one, and then that's it. But when they say all, that makes me think, okay, I got to keep going, but how long do I keep going for? So I just wanted to point that out. I mean, I think most people would get to 19 and say, okay, that's it, I'm done. But are you done? I mean, there could be more, right? Anyhow, so this is the only one. And of course, this one we found in the previous part. Determine the Kirk triplet for which cos of the angle ABC is as close to 0.99 as possible. So here we have our diagram as before, and what I'm going to do in this diagram is drop a perpendicular from A down to the base, like that, and this is of course a right angle since it's a perpendicular. And when you do that, this side of course just becomes y divided by 2, because that perpendicular will cut BC in half, because this is an isosceles triangle. And then now we know as before that this is 60 degrees, correct? And we can now proceed with this question using this triangle, which is essentially a 30, 60, 90 triangle. Now in a 30, 60, 90 triangle, as I'm sure you all know, the ratio of the sides are 1, 2, and root 3, like that. Now we know that this is z right here. So we can get the other two sides in terms of z. This side, of course, will just be z over 2 using those ratios. And this side will be root 3 z over 2. This side right here from A down to the base. Okay? And then now what we can do is concentrate on this angle right here. And from that angle, we know that the cos of angle ABC is going to be, in terms of our basic trigonometry, adjacent over hypotenuse. So our adjacent is y over 2, and our hypotenuse is x. Now, unfortunately, we have this in terms of two variables, y and x. If we can get them in terms of one variable, then we can solve for this, because we know that this is equal to 0.99. See, currently we can't solve for it because we've got two variables. But if we can get one variable instead of two, we can solve for that in terms of a numerical value. So that's our ultimate goal. But how do we reach that goal? Well, you're going to have to concentrate on this triangle right here. This one that I'm circling in blue. That is, of course, a right triangle, so we can use Pythagoras. We have y over 2 squared plus root 3z over 2 squared is equal to x squared. Correct? So this becomes y squared over 4 plus 3z squared over 4 is equal to x squared, like that. If you multiply through by 4, you get y squared plus 3z squared is equal to 4x squared. Correct? And then isolating for 3z squared, you get 4x squared minus y squared, like that. And if you factor this, you get 2x, y minus plus, like that. And at this point, you think, well, geez, that doesn't really look like it's going to help me. I'm still kind of wondering, how do I get any values for x or y? Well, this is one of those questions where you've got to use a little bit of inspection. So I'm going to make a table here, x, y, and then these two factors right here, 2x minus y and 2x plus y. And 2x minus y multiplied by 2x plus y is equal to 3z squared, correct? Now, since z is a prime number, these two must be some combination of 3z squared. So, for example, they must be 1 and 3z squared, or they could be 3 and z squared, or they could be z and 3z. Okay? Any one of those will give you a product of 3z squared. So if that is the case, we can now calculate for x and y. And the first one, if you add these two, this one and this one, if you add them, you'll get 4x because the y's cancel. And you therefore have to add those two, is 1 plus 3z squared. Correct? And therefore x is going to be 1 plus 3z squared over 4. All right, so I'll put that in here, 1 plus 3z squared over 4. And in a very similar way, I want to solve for y. Well, I'll take this and subtract from it that guy. And if you do that, you'll get 2y is equal to 3z squared minus 1, and therefore y is equal to 3z squared minus 1 over 2. 3z squared minus 1 over 2. Okay? And in a very similar way, I'll sort of save the algebra for you. In a very similar way, you can do the same thing for this guy and this guy. If you do that, you get values of x and y as follows. You will get z squared plus 3 over 4, z squared minus 3 over 2, and then for this one, you will get, interestingly, z and z. Okay? Now, remember one of the conditions, if you remember, of the question was that x has to be greater than z. So because of that, x cannot equal z, like here. So that cannot be used. So the only ones we can use are this guy and this guy right here. Those are the only ones that we can use. So I'll just put a box around that for x and y. Okay, so that takes care of that part of the question. So now that we have x and y in terms of one variable, namely z, we can go back and revisit this right here. And when you revisit that, that will help us solve for z and eventually for x and eventually for y. So this gives me cos of ABC is equal to y over 2 over x, and we have a numerical value 0.99, correct? And what I'm going to do is create a equation with our values of y and x. So first let's start with this guy right here. Y over 2, so it'll be 3z squared minus 1 over 2, but it's over 2 here also, so that would actually be over 4. So don't forget that. All right? And then it's over x, which is 1 plus 3z squared over 4. So if you invert and multiply, you'll get 3z squared minus 1 over 3z squared plus 1 is equal to 0.99. And if you break this up, 3z squared plus 2, or rather plus 1 minus 2, this will allow you to make a little bit of a neat rearrangement of this. This now becomes 1 minus 2 over 3z squared plus 1 is equal to 0.99. Bring this guy over to the other side, and you get 2 over 3z squared plus 1 is equal to 0.01, 1 minus 0.99. And then 2 over 0.01 is equal to 3z squared plus 1, right? And therefore this is 200 is equal to 3z squared plus 1. 199 is equal to 3z squared. And finally, z squared is equal to 66.3 approximately, and therefore z is equal to 8.1 approximately. So you think, okay, great, I've got a value for z, but the problem is that, first of all, it's not an integer. Z has to be an integer, and also, if you remember, z has to be prime. So we can't really use 8.1. But the nature of the question is that we don't have to use exactly as long as it's close to it. If you go back and read the question again, determine the Kirk triplet for which cos of ABC is as close to 0.99 as possible. So if we can get a prime number that we can make the cos of ABC as close to 0.99 as possible, then that will work for us. What we solved helps us figure out what that prime number could be. In this case, it's, in the vicinity of 8. So what prime numbers are in that range? Well, the closest one is 7, and there's another one, 11. Correct? I don't want to use 5 because 5 I've already used in the previous, and that gave us different solutions. Correct? So let's use 7 and 11 for z, and see what we get for the cos of ABC. If we use the value of 7, the cos of ABC, if you remember, it was y over 2 over x, and y over 2 over x we already got simplified right here, so don't need to do all the math again. So I'll just repeat that. It's 3z squared minus 1 over 3z squared plus 1. If you substitute z equals 7, you will get 146 over 148, and that is equal to 0.9864 approximately. Okay? In a very similar way, I will substitute z equal 11 and see what happens. That gives me the same equation right here. If I put in z equals 11, I will get 362 over 364, and that is equal to 0.9945. All right? Now, we're not done because we have to do the exact same thing for those two values, right? So, unfortunately, we still got a little bit more work to do, but that's okay. We can definitely do that. So this time y over 2 is z squared minus 3 over 4, and x is just z squared plus 3 over 4. Invert and multiply, and you will get z squared minus 3 over z squared plus 3. And then again, you can do a little bit of a rearrangement. Z squared plus 3 minus 6 all over z squared plus 3. This will leave 1 minus 6 over z squared plus 3. And remember, this is 0.99. All right, let's keep going here. Put that on the other side, the z squared plus 3, and then this becomes 0.01. 6 over 0.01 is equal to z squared plus 3. This becomes 600, z squared plus 3. And we are almost there. 597 is equal to z squared, and therefore z, if you take the square root of this, is approximately 24.43. Again, we don't get an integer, and we don't even get close to an integer or even a prime number, but we have to choose the prime numbers that are in the vicinity. And in this case, it looks like 23 and 27 would be the closest primes. All right, in a very similar way as we did here, let's figure out what is the value of cos ABC for z equals 23 and for z equals 27. So in this part of our question, our cos ABC was this right here. Okay, so it's just the same formula. Z squared over 3, Z squared plus 3. If I use Z equals 23, this becomes 526 over 532, which is equal to 0.9887. And if I use Z equal to 27, this would become 838 over 844, which is 0.9928. All right, now the heart of the question is, which one of these is closest to 0.99? 0.99, we have to get as close to that as possible. Which one is closest? Let's put them all on the same screen. We got this one, and these two over here. Just take a minute and figure out which one is closest in terms of a numerical value to 0.99. The answer is this one right here. So which z value did I substitute in the equation to get that? It was z equal to 23. So that is our z value. Now I just have to figure out the values for x and y. X is in that particular part of the question, z squared plus 3 over 4. Z is now 23, which is what we have established. And this gives you an x value of 133. Y is z squared minus 3 over 2. And for z equals 23, this gives you a value of 263. So finally, our ordered triple, Kirk triplet or triple, is 133, 263, and 23. There you have it. A Scolum sequence of order n is a sequence S1, S2 until S2n of 2n integers satisfying the conditions. For every k in 1, 2, 3 up until n, there exists exactly two elements, Si and Sj, with Si equal to Sj equal to k. And part 2, if Si equals Sj equals k with I less than j, then j minus I is equal to k. For example, 4, 2, 3, 2, 4, 3, 3, 1, 1 is a Scolum sequence of order 4. List all Scolum sequences of order 4. So first, let's understand this question. So we've got, first and foremost, a certain number of integers, correct? 2n integers. And they are saying that it's order 4. So if it's order 4, that means there are n equal to 4 in terms of that list. So 2n is equal to 8. Okay? So that's what that first part means. So the next part is that you've got all the numbers from 1 until n. So in our case, since n is 4, we have 1, 2, 3, 4. In this set, we have two elements, Si and Sj, where Si is equal to Sj, is equal to k. So what that means is that our list of elements, there's got to be two of each of these. So there's got to be 2 1s, 2 2s, 2 3s, and 2 4s, right? Because these are all equal. And that's what basically they're saying in that first condition. The second condition right here is indicating the order in which you place them in a row, for example. So for example, we've got 8 numbers, right? And we have to place them in order. So 1, 2, 3, 4, 5, 6, 7, 8 places. And I'll label it S1, S2, all the way up till S8. And this is the criteria. if you have Si equal to Sj, which is equal to k, so that means one of these is Si, one of these is Sj, and the k is one of these guys. Here is this criteria. J minus I is equal to k. So what does that mean? J minus I is equal to k. Well, it means that the positions, look at the positions. If you subtract the position number from one another, it will be equal to k. So for example, if the 1 is here and the 1 is here, S2 minus S1 is not what they're referring to. They are referring to the 2 minus 1, correct? That is what J and I are. So in this case, J is 2, I is 1, and J minus I is equal to 1. 1 is the value of the number I placed. You see what's happening there, I hope? And in a very similar way, for example, this is probably not going to create one of those sequences that they're asking for, but let's say we want to place 2. Well, I can put 2 here and 2 here. That will work. Why? Because if you look at it, it's S6 and S4. Here we get J equal to 6. Here we get I equal to 4. And 6 minus 4 is 2. And that is which number we placed. So I hope you kind of understand what's going on there. It's not really that difficult. I think it becomes a little daunting. These types of questions are that when you first read it, you think to yourself, I don't know how to do this. You just brush it off. You don't even attempt it. But if you just, in a very kind of confident way, read through it, take your time, work through this, I promise you that you absolutely can. So here we go. We're going to do that same thing. We're going to take our time and try to find exactly what they're asking for. Okay, so they want all Scolum sequences of order 4. All right, we know that we've got 8 positions, just like that. S1, S2, all the way up until S8. And we know that the numbers, since it's an order 4, are these numbers, but each of them is twice. So I've got everything set up where we are all set to go here. Now what we have to do is figure out, how do I place these 8 numbers into the sequence, matching the criteria. Okay? All right, what strategy am I going to use here? Let's see. Well, first and foremost, they gave us one of those, right? They gave me one right there. So since they already gave me one, I'll just put that in there. Might as well, right? Take whatever information that they give us. Okay, so this is the first one. I don't know how many there are, but this is the first one. Now, the first thing I noticed with this one is that the ones were placed here, S8 and S7. And that's fine, right? Because 8 minus 7, this minus this, which represents J and I, is equal to 1, which is indeed that number. Correct? So, I'm sure by now you get it. I don't need to keep laboring this every single time. Otherwise, it's going to be brutal in terms of its repetitive nature. So I just want to make sure that you understand that. If you do, we'll move on with this. So the first one we got. All right, let's move forward here with our second one. So the first one, they concentrated on these two to place some numbers. Now what I'm going to do is, just keeping in that sort of format, I'm going to also concentrate on S8. They started with S8. I'm also going to start with S8. I have to start somewhere, right? But I obviously am not going to use S8 and S7. They already used those, so I'll use S8 and S6. Okay, why not? So that means my J and my I are 8 and 6, which is equal to 2. So that means 2 has to go here and here. Okay? And now I've got to sit here and try to figure out where everything else goes. So this is really just trial and error. We've got to sit here and figure this out. Okay, no problem. How about the next number? Let's say if I put a 3 here, then the other 3 has to go 3 positions away, correct? Because s minus something has to equal 3. And that would be 4. So the 3's got to go here. And then I've got, 4 and 1 remaining. So if I put the 4 here, it's got to go another 4 positions. 5 minus something has to equal 4. So that's going to be 1. So the 4 goes there. And the 1s can go there. That works out. Okay? So we got another one. And following the same tradition here, I will again start with S8. But instead of 7 or 6, I'll this time use S5 as my first position. Well, S8 to S5, 8 minus 5 is equal to 3. So those have to be 3's. Correct? And then now I've got to, trial and error, figure out where everything else goes. Well, as this is 4, this is S7, right? So it's got to go 3 units down. So it's got to be S3. So this is S3. So the 4 goes here. And then the 2's probably here, S6 and S4. That would work because those are 2 units apart. And then finally the 1's can go there. And then keeping in the same tradition, let's just keep going here. S8 again. Keeping in the same tradition, I'm going to look at S8 again. But instead of S7 or S6 or even S5, I'll look at S4 as my possible next position. So S4 is here. Well, that's pretty straightforward. If you've got 8 and 4, these have to be 4's. Correct? And then now you just have to figure out where the other numbers go. If this, for example, is 2 for S7, this has got to be 2, S5. If this is S6, then this has got to be where the 3 goes, namely S3, and therefore the 1's go here, S1 and S2. All right, and then after that, we can't put any more, because if I start looking at S8 and S3, I would have to put 5's there, and we don't have any 5 in our set. So we are done. But there's always a little bit of extra, right? Something that a lot of people miss. Even I would miss it, to be honest with you. I'm not going to pretend that, oh yeah, I know this. That the reverses also work. So basically that means that whatever order it's in, if I put it in the reverse order, like for example the first one, 1, 1, 3, 4, 2, 3, 2, 4, that will also work as a Scolum sequence. Okay? So this would be 2, 3, 2, 4, 3, 1, 1, 4. This one, if I reverse it. If I reverse this guy, it'll be 3, 4, 2, 3, 2, 4, 1, 1. And finally, if I reverse him or her, 4, 2, 3, 2, 4, 3, 1, 1. All right. So I think that I hammered that home good enough. So how many do we get? We got 1, 2, 3, 4, 5, 6, 7, 8 of them. So we got 8 Scolum sequences of order 4. Determine with justification all Scolum sequences of order 9 which satisfy all of the following 3 conditions. S3 is 1, S18 is 8, and between any 2 equal even integers, there is exactly 1 odd integer. So we have this time order 9. So that means n is equal to 9. And of course, therefore, 2n is equal to 18. So we have 18 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, we've got the same ones listed once more. And we have to place these in an order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. And I will label these S1 all the way up to S18. And now let's begin. So they gave us S3 is equal to 1. Okay, it's nice and helpful there, I hope. And they told us that S18 is 8. And then we've got this one here. Between any two equal even integers, there is exactly one odd integer. Okay, well, let's move forward here and see if this third clue pops up, how it helps us. Not entirely sure right now, but let's see. Well, S18 first and foremost is equal to 8. And therefore, we know where the other 8 is going to be placed. The first one is here. The second one must be right here. Why? Because 18 minus 10 is equal to 8. So hopefully by now you've become an expert on this question by doing part A, I guess, so far. So the 8 must go here. All right? And then the 1 we don't know, right? It could go here or it could go here because both of those positions are possible. So I don't really know about the 1 quite yet. So I'll leave that alone. And now you stare at this and you think, well, geez, I don't know where to go from here. But this is where this comes in. Between any two equal even integers, do we have so far two equal even integers listed in our sequence? And the answer is yes, we do. We have the 8s. Those are two equal even integers. Between them, there is exactly one odd integer. So that means in this region, from S11 all the way to S17, there is only one odd integer. That is in my opinion, the heart of this question, the understanding of that fact. Only one odd integer can be placed there. All right, well, which one? Which one of the odd integers do I place there? I've got 1s, I've got 3s, 5s, 7s, and 9s. Those are my odd integers. Which one of those can I place? I can only place one. Well, let's think about this. Can I place a 1? Well, no, because the 1, I actually just talked about it about a minute ago. The 1s have to go all the way over there in order to satisfy the conditions of the Scolum sequence. So 1 can't be 1. All right, so let's get rid of that. Can it be 3? Well, if I put a 3, perhaps, right? I could put a 3 here, a 3 here. You're hoping that there would be an obvious answer, but unfortunately there isn't. How about a 5? Well, same thing. I could put it there. Perhaps it could go here. Oh boy, that's not helping me either. And you're starting to get a little discouraged, right? Same thing with the 7. Well, geez, I don't know. But the 9, I'll tell you why. Because the 9 has to go in here. Why? Well, because where else could it go? If you put it here, the only other place, it has to be 9 away from 9, right? Which is 0. There's no S0. Correct? If you understand this question in terms of how these numbers are placed, you'll realize that the 9 cannot go anywhere in here. So the 9 must be somewhere in here. Right? Somewhere in there the 9 has to be. Now at this point, I don't know where, so I'll just put that 9 here. When I say here, I don't mean like in that position. I mean just I'm placing it there to kind of emphasize that it's somewhere in there. Actually, you know what? I'll put it here. I think a little bit better to put it there. So I know that the odd integer that they are talking about in that second sentence, or second part of the sentence, I guess, is 9. Okay, that's great. But what about the other numbers? Well, those have to be even then, since there's only one odd integer allowed in that part of the sequence. Okay, what are the other even integers? The even ones are the 2s, the 4s, and the 6s. The 8s are already used up. Okay, so I'll circle the other 8. So I got 1, 2, 3, 4, 5, 6 even integers. And how many places do I have? 1, 2, 3, 4, 5, 6, 7. But one of them is already taken up by 9. So that basically means that all 6 of those have to be placed here. That's interesting. Okay, let's do it. Let's try to fit it in. Let's start with the 6s. If a 6 goes here, then the other 6 has to be 17 minus 6, which is S11. All right, so this other 6 has to go there. If the 4 goes here, the other 4 has to be 16 minus 4, which is S12. All right, 4 goes there. And then we got to put the 2s. Well, the 2s got to go there, and therefore the 9 must go here. All right, great. So we are, really moving along here. We're done with the 2s, we're done with the 4s, we're done with the 6s, we're done with the 8s, and we're done with one of the 9s. So I'll just circle one of the 9s like that. So I've got 1, 2, 3, 4, 5, 6, 7, 8 spaces left. And I hope I have 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I forgot to circle one of the ones. I was getting worried there. I said, oh, geez, I messed up again. Okay, so let's try this again. 1, 2, 3, 4, 5, 6, 7, 8 spaces left. And how many numbers do I have? I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, perfect. Okay, now let's figure out where these other numbers go. All right, this is at this point, really, it's to be honest with you, it's just trial and error. I don't think at this point there's any hard and fast rules. We just have to plug away at this. All right, let's do that. Let's start plugging away. Where do I even begin here? Well, let's start with the 9. The 9 can be the easiest one to place. S14, so the other 9 has to be 14 minus 9, which is S5. All right, great. So that's done. Okay, that was the only one that was easy, I think. Where do I go next here? I don't know. Let's start with the 7s. See if I can place it. If I put a 7 here, the other 7's got to go S8, right? Okay. All right. And S2, well, the 1 has to be here or here. So let's say the 1 is there. That would work, but let's just see what happens. Now for S4, well, I got 5, so let's see if I put a 5 there. That means the other 5 would be S9. Okay, so far so good. Oh boy, the 3's don't match, right? Because that's only a difference of 1. All right, no problem. No problem. That's what trial and error is all about. Let's try again. Okay, well, the 9 we know for sure. That's the only one we know for sure. Let's try again. 7. And then 7's got to go here. All right. This time, I'm not going to put the 1 there. I'm going to put the 1 here. Let's see if that changes my luck. Okay, so far so good. The 5, okay, let's put the 5 there. That means the other 5 has got to go S7. And yay! That works. 9 minus 6 is indeed 3. Perfect, we got it. So this is the Scolum sequence that satisfies these 3 conditions. All right? So I really hope that my take-home message is it's a hard question, right? I agree with you that it's a hard question. But if you approach it with confidence and really just work at it, especially in practice, you absolutely can figure this out. I know when you read it, it's daunting. You think, oh, jeez, I don't know this stuff. I don't even know where to begin. I completely get it. And trust me, there was a stage when I was in that type of frame of mind also, where I would get to the hardest questions and not even attempt them. But with a lot of practice, a lot of time, a lot of effort, I was able to improve. And that's really, there's no secret, there's no magic, there's no trick. It's just a lot of hard work. Okay? And we have one more part. We have part C also to this question. Prove that there is no Scolum sequence of order n if n is of the form 4k plus 2 or 4k plus 3, where k is a non-negative integer. So instead of dealing with k's, because that's going to get confusing, I want to explain this using a number. And that's perfectly fine in my humble opinion. So instead of using, k's and getting all abstract, which will confuse everybody, I'm just going to use a certain number. So for example, I'll just let k equal 1. All right? K equal 1 throughout this question. Why not? If you can show it for k equals 1, then it should be sufficient for all k's, right? I mean, you can show the main scheme or the main concept of the question with a numerical value, then you will understand how the question is for all the numbers. So if k equals 1, on the first one we got 4k plus 2, which of course would therefore be equal to 6. That will be my n. And in the second one, if k equals 1, 4k plus 3 will be n equal to 7. Okay? So I will prove it for both of these, and we'll take it one step at a time. So we'll do the first one, and then we'll do the second one. The second one will be pretty much identical to the first one, so you'll definitely get the hang of it. If n is 6, that means we've got numbers 1, 2, 3, 4, 5, 6, and we've got them listed twice. Correct? All right. Now, in the proof or the explanation, we have to concentrate on even and odd numbers. In our case, how many evens do we have? Well, we got 1, 2, 3, 4, 5, 6. We've got 6 even numbers. And how many odds do we have? Well, we've got, same, 6 odd numbers. All right? So far, you're following, right? No problem. Now, when we put in those numbers into our sequence, you remember our sequence? This is how many? 12 of them, right? So it's going to be S1 to S12. Now, when you place a number, where do you place it? Right? That is the key to the understanding of this question. So first, I will start that conversation with even numbers. Let's say I have an even number, correct? And let's say that even number, I'll just use 2 as my example. An even number, so for example, 2. If I put 2 somewhere in here, if I put it there and I put it there, notice that those 2 numbers are even position numbers. Even position numbers. Correct? Because 12 is an even number and 10 is an even number. Agreed? Okay. So I'm going to do this slow so you understand. But can I place the 2 anywhere else? Yeah, I can. It's not that those are the only places I can place 2. I can place 2, for example, here and here, because 11 minus 9 is 2. So I've got now odd position numbers. Now you say, well, then, okay, well, how does that help me? You've got odd, even position, odd positions, the odd, even positions. Where is this leading? Well, pay attention. For an even number, for example, 2, I need to choose 2 even positions, correct? Or I need to choose 2 odd positions. Okay? So that is the heart of this question. Now, how many even numbers do I have in this example? I've got 6 even numbers, right? So that means I have to choose 2 for each of those numbers, correct? So in total, for 6 even numbers, I would have to choose, for example, 6 even positions, correct? Or 6 odd positions. So I'll make a little table and list that. So either 6 even, and I'll give you an example of what I mean. They could be S2, S4, S6, S8, S10, and S12, right? For example, if you're putting the numbers 2, 2, 4, 4, 6, and 6, those are our 6 even numbers. The 2 could go here, the 2 could go there, right? Because 4 minus 2 is equal to 2. The 4 could go here, the 4 could go there because 12 minus 8 is equal to 4. Or if you're putting 6's, you could put the 6 here and the 6 here because 12 minus 6 is equal to 6. Correct? Or another possibility, is you can have 4 even position numbers and 2 odd position numbers. So for example, you'd have S2, S4, S6, S8, and then you'd have S1 and S3. Correct? The 2's could go here because 3 minus 1 is equal to 2. The 4's could go, let's say, here and here because 8 minus 4 is equal to 4. And the 6's could go here and here, something like that, right? Any kind of combination. But the take home is that it's either 6 even, 4 even, or 2 odd, or it could be 2 even and 4 odd, the position numbers. Or it could be 0 even and 6 odd. I'm referring to the position numbers. So again, for this one, an example is S2, S4, S1, S3, S7, S11, right? And for all odd position numbers, it'd be S1, S3, S5, S7, S9, and S11. Okay? And I think, okay, well, I understand, but where's this leading me? All right, we haven't talked about the odd numbers yet. When I start talking about the odd numbers, hopefully, I hope this will all come together. We talked about the even numbers. Now let's talk about the odd numbers. How many odd numbers do I have in my original list? Well, these are the odd numbers, right? I've got 6 of those. So that means I've got 1, 1, 3, 3, and 5, and 5. So I've got 6 of those, correct? And now I want to figure out the possible position numbers. Where can I place them? And this is the key right here. Anytime you have an odd number, anytime, and if you go back and look at the positions, you are going to have the following scenario. An odd number, let's say it's 1. It's going to be like that, right? Because 8 minus 7 is 1. But notice, one position number is even, the other is odd. That's the only way odd numbers can be placed in the sequence. Let's try another one. Let's try 3. Let's put it somewhere else. I've got 3 goes there. The next 3 has to go 3 down, right? So 10 minus 3, which is 7. That's where the other 3. Notice we've got 1 even, 10 is even, and 1 odd. That's the only way that you can have an odd number placed, where one position number is even and the other position number is odd. So that means if I'm placing 6 numbers, the only way to do that is to have 3 even and 3 odd. The position numbers. All right? So for example, 3 even would be like S2, S4, and S6. 3 odd would be S1, S3, and S5. Okay? So, now let's go back and see what is the total that we have in our sequence. How many odd position numbers and how many even position numbers do we have? Well, we have 6 odd position numbers, correct? These ones that I'm circling. Oops, not that one. And we have 6 even position numbers. 2, 4, 6, 8, 10, and 12. So we have 6 odd and 6 even position numbers. And that's our total. 6 odd and 6 even. So if we are going to place our numbers, the possible position numbers have to add up to 6 odd and 6 even. All right, finally, that's the take-home point. But can we do that? Well, for the odd ones, we need 3 even and 3 odd. And therefore, what's left? Well, the total is 6 odd, 6 even. What would be remaining, if you take away 3 even and 3 odd from the total, would be 3 even and 3 odd. But none of these scenarios match that. So there's no way that you'd be able to place these in that. Does that make sense? There's no way you could place these 6 even numbers and 3 even and 3 odd position numbers. Okay, so therefore, because that is a contradiction, it proves that this cannot be done. And therefore, we have shown that there is no Scolum sequence of order n if n is of the form 4k plus 2. And in my case, I chose k equals 1. All right? And in a very similar way, I will save you the pain. You can show it for this 4k plus 3. And I chose k equals 1, and therefore n would be 7. In a very similar way, you can show the exact same argument or proof to show that it will not work for this scenario also. All right, so I hope that made sense. Practice this one in your spare time, that will help you fully understand this question.